Right? All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good to hear. All right, so this was so if you asked me over a week ago, I thought this would be the first day I'd be meeting you guys. So I made a lot of plans last week just because I thought we'd be off. One of those was poker. So I made plans to play poker with my buddies on Thursday night. But I was teaching, I was working, so I had to be late. But I felt really bad. So when I arrived there, it turns out they had all been waiting for like 90 minutes to eat before I got there. Because originally they had planned to meet up at 6:30. I'm like, oh, I can't get there until 8 because I'm working until 7 and things like that. So they were waiting for me to eat. I didn't bring anything, so I didn't bring any food because I just came from work. So I got free dinner that everyone else provided, which was great. And then we played poker, and then I won. And so I not only I was late, I got free food, and I took money from everyone. So I'm like, wow, this is a great day for me. But I'm sure they don't feel very good. So one good thing I think for me at least. And I was due though, so I haven't won poker for like 7 times in a row. So I was due for a win. So all right. So today, plan for today, we're going to continue where we left off last Thursday. So we were talking about the direct stiffness method. So we were about halfway there. So we're going to talk about boundary conditions today, which is kind of the last thing. And I have a couple examples to cover. So that should take us maybe about the first hour of class today. And then before we leave today, I wanted to start talking about truss elements, which is kind of the next big thing. Okay. All right, so some announcements. I originally had wanted to post the first homework assignment by today, but I just wasn't able to get to it. There's some stuff that happened this afternoon, so I'm going to work on it tomorrow. So it'll be up by hopefully by tomorrow afternoon. And I'm looking at a due date for next Friday for the first homework assignment. Or excuse me, next Sunday night. So due date for this class will be next Sunday night. That's what I'm in. Okay. So for the most part, I'm gonna try to keep the due dates on Sunday night. And I usually like to give you guys anywhere around between a week and 5 days to kind of work on the homework after we kind of finish a particular topic. So starting tomorrow, if you were to start the homework tomorrow, you'd probably be able to do about half of it. And then the other half of it, we're going to finish on Thursday, talk about next Tuesday, and so on and so forth. Okay. All right. Are there any questions I can answer before we get started for today? Okay. All right. So let's go and get started. And so last Thursday, we were talking about the direct stiffness method. And we introduced this method as kind of one particular implementation or one particular way to go about the finite element method. And so despite its name, there's actually multiple different ways to implement the finite element method. The finite element method is kind of a general term for just kind of any way to transform a differential equation to an algebraic. Okay. And the direct stiffness is kind of the first one that we talked about. We're going over it mostly for kind of educational purposes. The direct stiffness method doesn't have a lot of practical uses. But it's a good place to start, especially if you're kind of rusty on linear algebra, you're kind of rusty on a lot of these other mathematical concepts. Direct stiffness is a good place to start. Okay. So we went over kind of two main parts of the direct stiffness method last time. Okay. So the first thing that we talked about was the idea of element stiffness matrices. Okay. And so the idea with an element stiffness matrix is that if you have a particular element, you can form a matrix set of equations, a small matrix set of equations that kind of encapsulate the physics, kind of encapsulate the properties of that element. Okay. Okay? And what this matrix represents, remember what this matrix represents is kind of the relationship between kind of external forces or external forcing effects on the element and the element's corresponding response. And so in this case, we're for this class, we're focusing primarily on structural mechanics, and later on we'll be focusing on heat transfer. So a response in this case will be defined by how much the element will deform. Okay. And so, the one type of element that we've gone over so far is just a spring. Okay. And so a spring is about as simple of a structural element that you can think of. Okay? And so the idea with the spring is that you apply a force to the spring is going to deform. Okay. And we can capture that physics, through its element stiffness matrix. Okay. And so as we go through the direct stiffness method, we're going to be introduced to different types of elements. So the next element that we'll learn probably at the end of class today is a truss element, and we'll talk about how the element stiffness matrix for that is formed. Okay, but step one of the direct stiffness method is to form the element stiffness matrices for every element in your system. Okay, which kind of leads into the next step of the direct stiffness method, where for the most part, most of the time, you're going to be looking at systems with multiple elements, right? When we're first starting this class, you're talking about 2 elements, 3 elements, 4 elements, sometimes 5, 6 elements. But in practical sense, you'll see when we use ANSYS, you'll have meshes with hundreds of elements, thousands of elements. Okay. And so each of those elements are going to have its own element stiffness matrix. But in order to actually solve the system, you need to assemble it all together into one big linear system. Okay. So step 2 is assembly. Okay. And so in the assembly step, you're going to basically combine together all the element stiffness matrices all elements in the system. Okay. And what you're going to get at the end of assembly is you're going to get one kind of gigantic linear system. So I often call this the global linear system. And so the idea is to get kind of one big matrix set of equations. So, a linear set of equations that you can solve for the solution. And so oftentimes it's going to look like this. And so we're going to have, some big forcing vector is equal to some big stiffness matrix. And that's multiplied by some, deformation vector. Okay. And when you assemble it, so on rainbow up here. When you assemble it, so what you're going to see is that a lot of the element stiffness matrices are going to take up different portions of the global stiffness matrix. Okay, so it may look something like this, where each box here is one of the element stiffness matrices. Okay. So that was just about the last thing we went over. So, we learned how to, take each element, look at the nodes that it's connecting to, and then assemble that into the correct spot into the global stiffness matrix. Okay. Okay. So once you have the global linear system, it's a linear set of equations. And so ideally, each row in this matrix represents one equation, right? Um, and each entry in this vector right here, these are your solution variables. Okay, this is ultimately what you want to solve for, right? And so ideally, if you have a square matrix set of equations, you have an equal number of equations to equal number of unknowns, right? And so ideally, what you'd be able to do is you'd be able to take this system and solve, okay, using a computer. This is not a linear algebra class, and so I'm not going to be making you solve these systems by hand. That's crazy. Um, and so we'll solve these on a computer. Um, so ideally, you should be able to do this, right? So if you have the same number of equations, same number of unknowns, you should be good to go. Okay. But what we learned last time is that it's not quite ready yet. And so, if you try to actually solve the system, what you're going to get is that your matrix is going to be singular. Okay. And the main reason is that if right after assembly, just the way that assembly just always works in these cases, your matrix here is going to be symmetric. Okay? So you're not going to be able to invert it. Okay. And so before we solve, there is actually one step that we have to do. Okay? And this step is going to basically turn our linear system into something that can be solved. And that's step 3, which is boundary conditions. Okay? And that's where we left off. And so we're going to talk today about boundary conditions, what they are, what they represent, and how do we actually mathematically incorporate these into our global linear system. And then solving would be step. Okay. All right, so in a nutshell, that's kind of the 4-step finite element process. And so, element stiffness matrices is always, well, technically there's a step before this, which discretize, so find your mesh, but we're going to assume that that's made for us. So we're going to start with step 1, which is element stiffness matrix. Step 2 is assembly. Step 3 is boundary conditions. And step 4 is to solve using a computer. Okay. And so, this is basically gives you a preview for the majority of this class. And so, this class, we're going to be looking at different variations on this kind of 4-step process. So different ways to find the element stiffness matrix, different ways to apply the boundary conditions, different ways to kind of look at assembly too. But, this is kind of the finite element process in a nutshell. Of course, it's missing all the finer details, but, everything kind of follows this method here. Okay. All right, so that was mostly a recap of last time. Are there any questions I can answer on this before we move on to boundary conditions? Okay, all right, so let's start talking about boundary conditions. All right, so just to kind of remind you, boundary conditions, when we talk about those, boundary conditions are basically any external effects that are having an effect on your system. Okay. And there were 2 types of boundary conditions that we were talking about. So the first is a Dirichlet boundary condition. Okay. So a Dirichlet boundary condition, the way that you can kind of remember is that this directly specifies the solution value. We'll kind of see what that means mathematically in a second. Okay. The other type of boundary condition that we have is called the Neumann boundary condition. Okay. And so Neumann boundary conditions, you can think of these as kind of, I consider them to be kind of more forcing effects, so more low type of effects. Okay. And so Neumann boundary conditions, I would say they kind of more indirectly influence the solution variables. The key word, of course, here being indirectly, and we'll talk more about that once we get to it. Okay. Okay, so these are the two types of boundary conditions, and there's relatively simple ways to kind of identify that for a structural problem. But the bigger question that we have to answer is, how these are going to affect our system. Okay. Okay. So let me draw the example again, just so that we can kind of talk about it. And so if you remember from last time, we were kind of in the middle of this example, which is a two-spring system. And so we have a fixed wall on one side. Okay. We have a spring that's attached to that wall, and another spring that's attached to that. And then we have a force that's being applied on the end, just like that. Okay. So we have two springs that are basically connected in series. And we want to find out how much the springs are going to deform. Okay. All right. And so I want to look at this system here and identify where the boundary conditions are and how we can mathematically formulate. Okay. All right. So one thing you'll notice here is that I've labeled all the nodes, and so we have nodes 1, 2, and 3. Okay. And ultimately, what we're going to solve for are the displacements of each node. So D1, D2, and D3. Okay. Those are the variables that we're going to be solving for in our solution. Okay. So these represent the deformations of each node in response to the load. Okay. But of course, the boundary conditions that we have specified here are going to affect those deformations. Okay. Let's start on the left side. So let's start on node 1. Okay. We can see from this diagram here that node 1 is fixed to the wall. Okay. Right. It's either bolted there, it's nailed there, whatever. It's attached to the wall. Okay. And the thing about this wall is that we've been told in the problem that this is a fixed wall. Okay. So that means this wall is not going to move. Okay. And so if that wall is not going to move, that means node 1 is also fixed. And if node 1 is fixed, that means its deformation must be 0. So that means here that we know just from the diagram that D1 is equal to 0. Okay. All right. Another way that we can say this is that, based on the boundary condition, we're directly specifying the deformation of node 1 to be 0. So that sounds familiar, right? Because, if we, if we're directly specifying our solution variable, so we're forcing it to have a value of 0, that sounds a lot like our Dirichlet boundary condition. And in fact, this is exactly that. Okay. So this means that this is a Dirichlet boundary condition. Okay. So any fixed support, so in a structural problem, a fixed support means that you're setting the deformation equal to 0. That's going to be a Dirichlet boundary condition. Okay. All right. Pretty straightforward, right? And so that's pretty helpful. But now the question is, how do we account for this? So how do we actually factor this into our global linear system? Because ultimately, the reason we're applying these boundary conditions is so that we can actually solve our global linear system. Let me remind you of what our global linear system looked like. Okay. So in this particular problem, we have 3 nodes, and so our global linear system is going to be a 3 by 3. Okay. So we have F1, F2, F3 is equal to. This is after assembly. So after assembly, we have Ka, K minus Ka, minus Ka. Okay. In the middle here, we have a Ka plus Kb, minus Kb, minus Kb, Kb. Okay. These are zeros. We have D1, D2, D3. Okay. So this is what we had last time after assembly. Okay. All right. So remember what this matrix represents. This matrix represents a system of 3 equations and 3 unknowns, right? Each row in this matrix is a separate equation. Because if we were to perform the matrix vector multiplication, so let's say that we take this row, okay, and we multiply it by this column vector, right? We just take the dot product between those two vectors. That gives us that equation. And so that tells us that our first equation here is F1 is equal to Ka times D1 minus Ka times D2 plus 0 times D3. Okay. This right here is the first equation in our matrix. Okay. So all I did there was just perform the matrix vector multiplication. All right. And so of course you can repeat that for the second equation and the third equation. You're just multiplying the second row by that column, and then the third row by that column. Okay, so it's the same. But for now, I'm just going to show you the first equation. All right. The issue here is that our Dirichlet boundary condition also gives us an equation. It's a much simpler equation. Okay. And so our Dirichlet boundary condition is telling us that D1 is equal to 0. Okay. So how do we make this work out, right? And so it kind of feels like we should make room in the matrix for this equation. Okay. But this equation here seems like it's hard because it only has one variable, right? So how do we incorporate this into our equation or into our matrix? let me do this. Let me, to make it a little bit more clear, let me kind of expand this equation. And I'll kind of flip the 0 to the other side to make it a little bit easier to see. Okay. So this equation that I'm writing here is equivalent to the one that's right above it. So we have 0 is equal to 1 times d1 plus 0 times d2 plus 0 times d3. Okay. So this seems kind of silly, right? So why are we adding the 0 times d2 and the 0 times d3, right? Because if you take 0 times d2, that's just going to cancel it out, right? And so why are we bothering kind of missing like that? Well, let me give it to you. Let me give it to you in a slightly different form. Let me take this equation here. Let me separate the coefficients from the variables into a vector. Okay. Let me do this. Let me do 1, 0, 0. Okay. Multiplied by a column vector, d1, d2, d3. Okay. Now we're getting somewhere because now what we have here, even though it's exactly equivalent to this simple equation here, d1 is equal to 0, right? What we've done is we've put this into a form that looks very similar to our global linear system. Okay. So let's take this and let's actually insert it into our global linear system, and let's actually insert it into the first row. Okay. So what we're going to do is I'm going to replace the entire first row with this equation. Because our Dirichlet boundary condition is telling us that this equation here must be satisfied, so we must have d1 is equal to 0. So we have to factor this into our global linear system somewhere, okay? And the place that makes the most sense is the first row, because this is affecting d1, and so it should affect the first row, which is the d1 row. Okay. All right, and so our first row is right here. Okay. And so I'm going to replace this row with all the coefficients and all the numbers that we have over here. Okay. All right. So instead of F1, F1 is the right-hand side value. We're going to have a value of 0 there. Is that me?
Oh, sorry, I didn't know I was unmuted. Oh my God.
You're good. You're good. You're good. All right. All right. All right. So the first row is so the first entry is going to be 0 on that side. And then for all the other entries in that first row, we're going to replace it with all of these. And so we have a 1, a 0, and a 0. Okay. So it's going to be 1, 0, 0. Okay. All right, and so that's how you apply a Dirichlet boundary condition. So to apply a Dirichlet boundary condition, you write out the equation that it satisfies, and then you're going to replace a row in the linear system that corresponds to that unknown. Okay. Let me write that down. So Dirichlet. So that's what you're gonna have to do for a Dirichlet boundary condition is replace a row. Okay. Any questions on how we did that? Okay. All right, so that's Dirichlet boundary conditions. Okay. Next, we have our Neumann boundary conditions. Remember what I said about Neumann boundary conditions, that these are indirectly affecting our solution variables. All right, so the Neumann boundary conditions, they are going to have an effect. It's just not going to be as direct as Dirichlet, okay? Because in Dirichlet boundary conditions, we actually went in and modified, an entire row in the matrix. So not only the things in the forcing vector, but also the entries in the matrix itself. Okay. For Neumann boundary conditions, for the most part, we're not going to make any changes to the matrix. Instead, a Neumann boundary condition is only going to affect the forcing vector on the other side. Okay. All right, so let me go ahead and draw our linear system here again. Zero. Let's get a. Okay. All right, and so when I say that the Neumann boundary conditions are not going to affect the matrix, that means everything here. Okay. Neumann boundary conditions are not going to affect anything there. Okay. Where they are going to have an effect is right here. Okay. So what I've boxed in purple right here, this is our forcing vector. Okay. So our Neumann boundary conditions will only have an effect on that side. Okay. All right, so let me scroll back up here to our diagram for the problem itself for the springs. Okay. And so the place where we have a Neumann boundary condition being applied is on node 3. Okay. And so according to this diagram here, we're applying a tensile force F on node 3. Okay. In other words, we're applying a force F3 on node 3. Okay. So this tells us that a Neumann boundary condition is occurring on node 3. All right. Let's come back here. And so if we know that our Neumann boundary condition is being applied on node 3, okay, that tells us that the nodal force on node 3 yes.
So here you still have the first row replaced with the Dirichlet equation.
Yeah.
Do we keep it that way?
Yes, we do.
Okay.
Yep. Yeah, and actually that's the primary means that we're going to use to break the symmetry, right? Remember, it was kind of, we couldn't solve it before because this entire matrix was symmetric. But when you apply the Dirichlet boundary condition, it actually breaks that symmetry, actually makes it solvable. You actually need both. So you need both Dirichlet and Neumann to
I see.
yeah. Yes,
And how come D1 wouldn't be equal to 0?
it is equal to 0 here, but technically the way we set up this equation, everything here in this vector is still technically unknown. But we've changed that first row in the matrix to effectively force D1 to equal 0.
Oh, okay.
It's just we kept it out. We want to kind of keep the structure of the matrix the same. Yeah. Yeah. The main reason we do that is that D1 still affects the other variables. And so if you look at this coefficient here, D1 still enters into that equation onto the first term. So we still need to keep the D1 there for that reason. But we changed the entire first row to force it to be 0.
Okay.
Yeah, you'll see once we invert this matrix that D1 is going to be 0.
Okay.
Yeah. Okay, so from the diagram, we know that the nodal force on node 3 is F. Okay. And so from this, we can kind of automatically state that F3 is equal to F. Okay. So this is actually a much simpler change. And so in terms of the matrix, we just delete F3 right here. And then we change that to F. So Neumann conditions are actually much easier to work with because you don't have to replace the entire row. Just whatever force that you have, you just kind of slot it into that. You slot it into that force vector. Okay. And then by that same token, we know from our diagram that there's no force or anything being applied on node 2. Okay. This tells us that little f2 in our matrix is going to be 0. Okay. And so we can replace f2 with 0. Okay. So technically, you can say that node 2 also has a Neumann boundary condition of 0. That's one way to look at it. But if for me, what I see is that there's no force being applied there, and so I'm just going to put a 0 on that forcing factor. Okay. All right, and so from here, we can solve. And so if we look at this system here, right? Normally you would have numbers here. So of course I did everything in symbols here just because it was kind of just a walkthrough. But normally you would have Ka, so you would have Kb, and of course you would have F. These are all usually given to you in a problem. Okay. And so if you have numbers in all of these entries, and we've broken the symmetry, so there's no more symmetry in the matrix, so it's one that we can invert. This is one we can actually solve and get a solution for D1, D2, and D3. Okay. All right, and then the next step, of course, is done in MATLAB. So I have another example here to kind of walk you through the whole thing, and we'll kind of look and see how that's actually shown, how that's actually done in MATLAB. Okay. But before we jump into the next example, are there any questions on this? Okay. All right, so let's do another example. Okay, so for this example, we have a 3-spring system. And so just like the previous example, we're going to have a fixed wall. Okay, we're going to have one spring coming off from the wall just like this. Okay, this spring is going to be attached to a wooden block. Okay, and so we're going to assume that wooden block is rigid. And the reason that's important is that on this block, we're going to attach the other 2 springs. So we're going to have one spring up top here, just like that, and another spring on the bottom, just like that. Okay. But the fact that wooden block is rigid means that everything in that block is gonna move together. Okay. Okay. So let's go ahead and label all the nodes here. So we have one node that's attached to the wall. We have node 1 attached there. Okay. Everything on the block is going to move together. So I'm gonna call that entire wooden block. I'll call that node 2. And then we have 2 free nodes out here. So we have a node 3 and a node 4. Okay. All right. These 3 springs here are going to be all different. And so the first spring that's attached to the wall, we'll call that Ka. The second spring that's up top, we'll call that Kb. And then the third spring on the bottom, we'll call it Kc. Okay. All right, so we're going to assume that we have a tensile force, F3, being applied at node 3. And we're going to have a compressive force, F4, being applied on node 4. Okay. So F3 is going to the right, applied on node 3. F4 is going to the left, being applied on node 4. Okay. All right. So the big difference here is that I'm going to give you numbers for these. And so we're going to say Ka. Ka has a value of 500 Newton per meter. Okay. Kb has a value of 100 Newton per meter. Okay. Kc has a value of 250 Newton per meter. Okay. F3 has a value of 100 newtons, and F4 has a value of 50 newtons. All right. So here's our system. So we have 3 springs, 4 nodes, 2 forces, and 1 wooden block. Okay? And so what we want to do in this problem is we want to use the direct stiffness method. Okay? And we want to solve for the deformation of all 4 nodes. Okay. So we're going to follow the same process that we did from the last example, except, this time we have numbers, so it's a little bit easier to visualize. And we're going to go just a little bit faster just because, we've kind of seen the whole process. So we're going to go through element stiffness matrices. We're going to assemble. We're going to apply our boundary conditions. And for the first time, I'll show you how to solve these systems in MATLAB. So technically, it's our first exposure to MATLAB, but it's very simple. It's just a couple lines of code. See. Okay. We're basically just using MATLAB as a glorified calculator at this point. Any questions on the setup for the problem? Okay, all right, so let's go ahead and get started. So step 1 is element stiffness matrices. Okay. So we have 3 elements here. So we have Ka, Kb, and Kc. So let's do element A first. Remember, the most important thing about the element stiffness matrices is to note which nodes the elements are connected to. Okay. So if you look back up at the diagram here, element A, Ka, is connected to node 1 on the left and node 2 on the right. And so that tells us the element stiffness matrix is going to be F1, F2 is equal to Ka minus Ka minus Ka, Ka, D1, D2. Let's go ahead and plug in the numbers for this. And so we have, because we have values for Ka and, just Ka. We have F1, F2 is equal to, Ka has a value of 500. So we have 500 minus 500 minus 500, 500, D1, D2. Okay. Let's do the same thing for element B. So element B, if we go back up the diagram, is connected to nodes 2 and 3. Okay. So we have F2, F3 is equal to KB. KB has a value of 100. So you have 100 minus 100 minus 100, 100. Okay. D2, D3. Okay. And then we have element C. So element C will be an interesting one to assemble because you can see here that on the left, element C is connected to the wooden block. And so the wooden block is technically node 2. Okay. And on the right side is connected to node 4. So element C here is actually going to be F2, F4. The spring constant for element C is 250. So you have 250 minus 250 minus 250, 250. Okay. And then D2, D4. So this is the first time that we have an element with node numbers that aren't consecutive, and so we'll see how that affects the assembly. Okay. All right, but that's step 1 complete. So step 1 is kind of usually more annoying than difficult. It's just a lot of writing that you have to write down all the steps. Any questions on this step here? Okay. All right, so step 2 is going to be assembly. So now that we have these 3 element stiffness matrices, we need to combine them into one linear system so we can solve it all together. Okay, so since we have 4 nodes, our global linear system will have it'll be a 4 by 4. So four rows and 4 columns. Spell columns. Okay. All right, so on the left-hand side, we have F1, F2, F3, F4. F1. Oh, let me go by D actually. D1, D2, D3, D4. And the rows here, we have D1, D2, D3, and D4. Okay. So there is our global linear system. Four rows for 4 equations and 4 columns for the 4 unknowns, D1, D2, D3, D4. Okay. So the first step here is inserting these into the appropriate places. Okay. So if you remember how to do that from last time, we're going to look at the nodes that they each follow. All right, so I'm on the iPad here, so I have the benefit of color. But if you're taking notes on with pencil and paper, it's a little bit more difficult. But let me use the color here. So let me say element A. Call this orange. Okay. Element A is connected to nodes 2 and, or excuse me, 1 and 2. Getting ahead of myself. Nodes 1 and 2. Okay. So that means our element stiffness matrix for A is going to take place on the first 2 rows and the first 2 columns where those 2 intersect. Okay. So first 2 rows, first 2 columns, that's basically this box right up here. Just like that. Okay. So let's go ahead and insert the entries here. So we have a 500 minus 500 minus 500 and 500. Okay. All right, next we have element B. And so if we look at the element stiffness matrix for element B, we know element B is connected to nodes 2 and 3. So that's going to be the second row, second column, or second row, third row, second column, third column. So where all of those intersect. Okay. That's going to be this right here. Okay. We have a nice little kind of continuous box. Okay. So once again, we're going to write in the entries for element B. Element B, the spring constant was 100. Okay. Then remember, whenever we have overlapping boxes, we simply add it. Okay. And so this in this top left corner, we're going to have a plus 100. Okay. Then a minus 100, minus 100, and then a 100. Okay. All right, and then finally we have element C. So element C is the interesting one. So element C is connected to nodes 2 and 4. So unlike our first two boxes here, 2 and 4 are not directly next to each other in the matrix. And so we're going to have the second row, the fourth row, and the second column and the fourth column. Okay. And so if I were to box it out, it would look something like this. And so we have the second row, or second row, second column. That would be where this one is right here. Okay. Then we have the second row and the fourth column. So second row and fourth column is going to be this one right here in purple. Okay. Then we have the fourth row and the second column. Okay. So that's going to be that entry right there. And then we have the fourth row and the fourth column, which is that entry right there. Okay. So sometimes this could happen. And so sometimes when you insert your element stiffness matrices into the global matrix, it may be separated from each other if the nodes are not kind of contiguous. And that's totally fine. And so, you just have to kind of make sure that you're putting the entries in the right row and column. And this is kind of, I think, the main difficulty with the direct stiffness method is that, for now, this one's okay. So 4x4 system, it's kind of easy to keep track of what's going on. But eventually, when we get to truss elements, 2D truss elements, beam elements, frame elements, especially, your matrix might be something that's like 16 by 16. And that's much more difficult to kind of keep track of kind of where everything is. And so these problems, I always tell people that these problems, once you kind of get the method down and you have all the steps in your head, it's not the most difficult thing. It's mostly just kind of just kind of rinse and repeat. Where these problems kind of get you are in the details and making sure that you put things in the right place, you put the values correctly, you make sure things are negative or positive, and so yeah, that's where they get you. So and the problem is, if you make one small mistake, so let's say you move an entry, to the left just by one, it's actually going to give you, it'll look like a catastrophically wrong result. But in reality, you just kind of made one small mistake. And so that's kind of just the nature of these problems, which I wish there was kind of a better way, but that's that's just how they are. Okay, so let's go ahead and add in the values from element C. Okay. So the spring constant for element C is 250. Okay. So on the overlap box, we're gonna have a plus 250. We're gonna have a minus 250 on the off corners. And then we're gonna have a positive 250 on the bottom, just like that. Okay. All right, and then every place that's not boxed, that's not part of an element stiffness matrix, remember, we're just gonna fill them out with zeros. And in fact, we can go ahead and replace this. And so instead of, just 500 plus 100 plus 250, we can go ahead and just evaluate that. And so that's going to be 850 in that box right there. I'm used to different colors. Okay. All right, any questions on this? Okay. All right, so now that we've assembled, the next step is to apply our boundary conditions. We have three boundary conditions in this case. Okay. So let me scroll back up to the diagram so you can kind of see, right? And so on the one hand, we have a Dirichlet boundary condition on node 1. Node 1 is fixed to the wall. So that tells us that we're going to replace the first row in the matrix. Okay. Whereas on the other side, we have node 3 and node 4. Okay. Both of these nodes have an external force being applied, and so we have Neumann boundary conditions on nodes 3 and 4. Okay. And we have the actual values of F3 and F4, so that makes it pretty simple. Okay. All right, so let's go ahead and apply these. So our first boundary condition that we're going to apply is a fixed support or a Dirichlet boundary condition on node 1. Okay. So remember how we do Dirichlet boundary conditions? We're going to replace that entire first row. Okay. We have this first row right here. Okay. Since we're modifying D1 in this case, that means that the first column here, okay, the D1 column of the D1 row, we're going to put a 1 there. Okay. Every other entry on that row, we're going to make 0. Okay. So on the D2 column of the first row, that's going to be 0. Okay. Luckily, the D3 and D4 columns are already 0, so we don't really have to do anything there. Okay. I just traced over it for emphasis. Okay. Okay. And Dirichlet boundary condition means that we replace the entry in the forcing vector as well. So we're going to have a 0 on that entry there. Okay. Okay, so that's going to be our first boundary condition, the Dirichlet. Okay. So whenever you have a Dirichlet boundary condition, you first thing you do is you go to the row where that boundary condition is being applied. You put a 1 on the diagonal of where that Dirichlet boundary condition is being applied, and every other column you put 0. And then in the forcing vector, you're going to put a 0 there as well. Okay. All right. Now we have the Neumann boundary condition. So we have number 2, Neumann BC with value 100. Okay. And that's being applied on node 3. So we're going to go to the F3 entry. So our Neumann boundary conditions do not affect the matrix in any way. They only affect the forcing vector. Okay. Okay, so we're going to change our F3 here. We're going to replace it with the value for F3. And so F3 has a value of 100. Okay. We're going to put that there. And then our third boundary condition is a Neumann. So we also have a Neumann boundary condition on F4. But if you look at our original diagram, okay, you'll see that F4 is actually being applied in the opposite direction. So F4 is actually being applied to the left, where F3 is being applied to the right. Okay. So we need to make sure that we respect that sign convention. So we have to basically make sure that if we're defining the right-hand side or the right-hand direction as a positive x direction, okay, then F4, which is kind of pushing to the left, we have to make sure we make that negative. Okay. And so in our matrix here, instead of F4, we're going to have a minus 50. Okay. Where we made that minus because that F4 is going in the opposite direction. Okay. And then final step, of course, F2. We don't have any force being applied in F2. We have no Dirichlet boundary condition. And so we're just going to make F2 is equal to 0. Okay. So no. Why here? All right, any questions on how we apply the boundary conditions to this matrix here? Okay. All right, and so now we're ready to solve. And so now we have this four equation, four unknown system. Okay. So I will say that, you know, if you do want to solve these by hand, by all means you can go for it. You know, it's just you know, normally these problems kind of take more time than it's worth. And so so usually I say that, you know, you can do these by hand, but usually the juice is not worth the squeeze. And so, you know, normally it's better just to use a computer to kind of help you out with this. Yeah.
So if there is no boundary condition like stated in the problem, would we always just assume that it's 0?
No, so you're always going to get a boundary condition in the problem. It wouldn't be complete without a boundary condition. A system without a boundary condition would be just like a static object. So it would be like that chair. And so that chair right now, you know, it has no forces on it, so it's just not really doing anything. So,
Okay.
yeah, you can always assume that you have a boundary condition. Any other questions on this before we jump into the solution? Okay. So if you have a nice graphing calculator and you know how to solve these matrix systems of equations in your graphing calculator, I would say go for that. You know, those are you know, I think more and more people are starting to have them. You might even be able to put this online, honestly, somewhere. But let me kind of show you the way to do it in MATLAB, just because, you know, eventually we're going to transition to MATLAB as well. Okay. But this is not technically programmed, so this is kind of easy MATLAB. So I want you guys, you know, hopefully everyone has these matrices written down in their notes. So let me go ahead and transition to MATLAB here on my computer, just so I can show you how to solve this. And I definitely should have started up MATLAB before the class started. And of course, it's not installed. Great, Matthew Perry. Shit. Get out of here, Matthew Perry. All right, we're going to use an online calculator. Okay, so I'll link this exact one. I'm honestly just picking one off Google. But if you want to use the same one for your homework or anything, I'll link this to you. Okay. All right. So with this calculator, I'm honestly figuring this out on the fly here. Okay, so we need a 4x4 matrix. Okay. And so in this matrix, we're gonna enter the entries of the matrix that we just defined. And so our first row here is gonna be 1, 0, 0, 0. Okay. Second row we have is minus 500, 850, minus 100, minus 250. Okay. Next row is 0, minus 100, 100, 0. Okay. And our last row here is 0, minus 250, 0, 250. Okay. All right. Let's see. Actually, I don't think this does linear algebra. Let's see. Sorry about this. I was expecting MATLAB to be installed here, but I guess that's not the case. Let's see, online matrix. Takes me to the same page. Okay, here we go. Okay, this is perfect. And it's 4x4, so this is good. Okay, so here we're gonna enter our system, our 4x4 linear system equation. So one more time, I apologize. So we have 1. So this is gonna be the first row in our matrix. We have 1, 0, 0, 0. Okay. And on the right-hand side there, we're gonna have 0 there. Okay. Okay, and then on this side here, we're gonna have a minus 500, 850, then a minus 100, then a minus 250. Okay. And on the right-hand side there, we have 0, which is fine. Our next row here is going to be 0, minus 100, 100, 0. Okay. We are going to have an entry here on this side. This is going to be 100. Okay. So this is the F3 value right here. Okay. It's a little bit hard to see because the positions are swapped, but you can see I'm putting in the entries of the matrix here on the left-hand side, and on the right-hand side here, after the equal sign, this is where I'm putting the forcing vector. Okay. Okay. And then our last row in the matrix here, we have a 0, we have a minus 250, 0, 250, and on the right-hand side here, we have a minus 50. Okay. All right. And so if we look at this here, we have this here is our matrix. Okay. So this is our assembled matrix with all the values that we put in from before. Okay. And then on the right here, this right here is our forcing vector. So you can see here, this matches up what we had on the left in our notes. We have a 0, 0, 100, minus 50. Okay. Okay. Now let's keep it up. All right. So now that we've entered the entries into the matrix, we can go ahead and solve. And so I'm hoping this this solve button will do what I think it's going to do. Jesus Christ. Okay. Okay, good. All right. So this is the solution here. All right. So the solution here, you can see we have 0, 1/10, 11/10, and minus 1/10. So it actually does it in decimals, which is actually pretty nice. And so this first entry here is D1. The second entry here is D2, D3, and D4. Okay. And so if you equate that to decimals, and so that's what I have in my notes, we have D1 is equal to 0, D2 is 1/10, which is 0.1, D3 is 11/10, which is 1.1, and D4 is a minus 1/10, so it's a minus 0.1. Okay. All right, and I guess if you were curious, you can actually see the entire Gaussian elimination method, which is a little bit overkill. All we really cared about was just the solution here at the bottom. Okay. All right, so I need to contact IT and ask them about MATLAB in this classroom. Hopefully, you guys have MATLABs on your computers. But that's basically how you solve it. And so if you have a graphing calculator, you can do the exact same thing here. But I'll go ahead and send this link to everyone just so that you can have it as well. Right. Any questions on this process here? Yes.
So you must have both boundary conditions to solve this problem?
Yes, you need the Dirichlet and the Neumann boundary conditions.
So the right side was fixed, you can solve it?
Right.
You
So
only have to which the condition, right?
exactly right. So you need a Dirichlet condition, otherwise it's unsolvable. So physically, what that means is that if you don't have a fixed support and you apply a force, it's just going to have a rigid body motion. It's just going to deform forever or like that. You need the Neumann conditions because without it, you have no deformation because that's actually what's forcing the system. Yeah. All right. Any other questions on this here? Okay, all right. So we have 5 minutes left. I don't really want to start the next thing in 5 minutes, so we'll start Thursday with truss equations. I'll send this link to everyone, and hopefully we'll have MATLAB for the future. All right. So thank you guys for coming. Oh, question.
You can show us how to do it on that.
Yes. Yeah. So if once I get MATLAB working, hopefully by Thursday, then I'll go ahead and redo this one with MATLAB so I can show you. Yeah. All right. So thank you guys for coming today. Hope you guys enjoy the rest of your evening, and I will see you guys on Thursday. Yeah. Exactly. Yeah. Yeah. Thank you.
Another question.
Sure.
So I actually just got a new laptop and I don't have MATLAB installed. Either you allowed to access it?
You should have access to it. So if you search a Cal State Fullerton MATLAB, clear these drops here. So it is a software that the school's already purchased for everyone. So you follow the instructions on here, you basically log into MathWorks. I think you can log in with your Cal State Fullerton account. Yeah, your Cal State Fullerton portal username and password. So it'll take you to MathWorks and you can download the latest version of the math.
Sounds good. All right, thank you.
Yeah. Mhm.